Just ask Prajwal Gowda to join again. There was some technical problem. Just ask Prajwal Gowda to rejoin again. Somebody call him and inform him. Sagar, Sai Prakash, Samir Ahmad, Sania,
Present, sir.
okay, Sanjay, Sankalp, Sanket, Shiraj, Shivananda Natikar, Shraddha,
Present, sir.
okay, Shubham,
Present, sir.
right, Sumit, Suraya Banu, Tejas, Vivek,
Yes, sir.
okay, Yamunappa, Yamunappa, गांवकर रजत रामचंद्र, मंजुनाथ, प्रथमेश, जोसलिनो, सोहम, अतिया, Mohammad Mazhar joined. Anybody else joined?
Sir, 11, sir.
Okay. 11, Prajwal
Mohammed
Gowda.
Yes, sir. Prajwal Gowda.
Okay, right. Fine. Okay. In the last class, we were discussing about the assignment questions. Let us continue with the assignment questions, remaining ones. So this is assignment question number 13. Assignment question number 13. They have given the value of IE. I hope everybody are able to see the screen. Screen is
Yes, sir.
visible.
Visible, sir. Yes, sir.
Okay, fine. So slightly in the assignment question, I have changed the value there. Slight change in the values of IE, HFE, HOE, and HOB. But it's a similar problem. Slight change in the values. So like that, the values can be changed and given. So you have to read the question, understand, right, and then write the given data and solve the numericals. So IE is equal to 2.5 milliampere, HF is equal to 140, HO is 20 microsiemen, HOB is 0.5 microsiemen. Right now, here this instead of giving it as microsiemen, they may give it as micromho. Mho is the unit of admittance, or siemen is the unit of admittance. Okay, either they may give as microsiemen or micromho. Okay, all are one and the same. Right. So these given values, they are asking to find common emitter hybrid equivalent circuit and common base RE model. Now, how is the common emitter hybrid equivalent circuit? You should have that in your mind, right? Here there will come the resistance HIE, right? Then here will be beta IB, the collector current beta IB. Then here comes the output resistance, that is 1 upon HOE. So this rough idea you should have in your mind, that the common emitter hybrid equivalent circuit will be like this. There is HIE here, right? Then here is beta IB, the controlled current source, and at the output we have the R0 output resistance, or that is 1 upon HOE. So if we have this circuit in mind, right, keeping this circuit in mind, we have to find HIE, then this controlled current source, and this 1 upon HOE. So you are supposed to find these three values. So let us find these three values. If we want to find HIE, HIE is nothing but beta RE. HIE is in hybrid model. In RE model, it is beta RE. Right? We know the relationship between hybrid parameter and the RE parameters. So here, if you want to find HIE, we should know beta and RE. Beta is given, that is HFE. HFE is also called as beta. HFE and beta both are one and the same. HFE is in hybrid parameter, beta is in the RE model. Okay. Then beta into RE. So if we know beta into RE, then we can come to know HIE. But we don't know RE. So let us find RE first. According to standard formula, RE is given by 26 millivolt by IE. That is 26 millivolt divided by IE is given 2.5 milliampere. Just substitute here. That will be 10.4 ohms. Now substitute RE in this formula. HI is beta RE. It is 140 into 10.4 ohms. That will be 1.456 kilo ohms. Similarly, Next, let us find, we found out RE, then HIE. So what all are required here? RE is required, HI is required. This is beta. Beta IB is nothing but HFE. HFE is 140, that is beta. So write it here, 140 IB. Then let us find R naught, that is 1 upon HOE. So R naught is 1 upon HOE, that is reciprocal of admittance is the output resistance. The HOE is given, that is for common emitter configuration. The output admittance is given, HOE parameter is given. So 1 upon 20 microsiemens, that comes out to 50 kilo ohms. Right? For common emitter it will be HOE, for common base it will be HOB. Clear here? So like this we found out the output resistance, that is 50 kilo ohms. Next, draw the common emitter hybrid equivalent circuit. It is here, it is HIE. We have found out the value of HIE 1.456 kilo ohm. Then beta IB, that is HFE IB 140 into IB. Then R naught value we have found out 1 upon HOE, that is 50 kilo ohms. In parallel it will be with the controlled current source at the output. Okay, so this is common emitter hybrid equivalent circuit. Next is RE model. Second one they have asked, common base RE model. So that also rough idea should be there in your mind how the common base RE model will be, generalized common base RE model. So there is RE resistance here. Then as it is common base, we have alpha IE, right? We don't have beta RE for, that is for the common base, we have simply RE, and here it will be alpha IE. Right? For common emitter and common collector, we have beta IB, but for common base, we are having alpha parameter, right? Alpha, that is current gain for common base, so it is alpha IE. Then at the output side, it is R naught. At the output side, it is R naught, output resistance. So with the rough idea of these parameters in mind, this circuit in mind, common base RE model. So let us find RE. RE we have already calculated according to the standard formula, that is 26 millivolt by IE. So that is same, whatever they have given, it is applicable both for common emitter and common base. IE value, that is 26 millivolt by 2.5 milliampere, that is 10.4 ohms. So value of RE is 10.4 ohms. Next, alpha is approximately equal to 1. The value of alpha for common base configuration is approximately equal to 1. Therefore, R naught, let us find R naught, that is reciprocal of admittance. For common base, we have to consider HOB. Remember, common emitter it is HOE. So this E stands for common emitter. HOE for common emitter, HOB for common base, HOC for common collector. Okay, so HOB reciprocal of this 0.5 micro mho or microsiemens, that gives the value of the output resistance. So R naught is 1 upon HOB, that is 1 upon 0.5 microsiemens, that comes out to 2 mega ohms. Okay, so that is 2 mega ohm here. So this is the common base RE model. RE model for the common base configuration. Okay, so this is question number 13, right? That is common emitter hybrid model and common base RE model. Okay, let us move on to question number 14. Question number 14. It is approximate hybrid equivalent circuit of voltage divider bias configuration is asked. First, we have to know approximate hybrid equivalent circuit of fixed bias configuration. Okay, how we are getting the approximate hybrid equivalent circuit of fixed bias configuration? If we know this, then we will be able to explain the approximate hybrid equivalent model of the voltage divider bias. This is the fixed bias circuit or configuration, common emitter fixed bias configuration, or simply fixed bias configuration. There is a resistance RB, resistance RC, emitter is grounded. Input is applied through the capacitor C1 to the base terminal. Output is taken from the collector terminal through capacitor C2. Right? Then with RB, RC resistance and emitter terminal connected to ground, fixed bias circuit. This is the hybrid model, approximate hybrid model of the fixed bias configuration. Okay, how it is? So here this is RB. So VCC is connected to ground for AC analysis. So RB is in between base to ground. RB comes in between base to ground. Then HIE parameter, that is beta RE, that comes here for the emitter base junction, HIE or beta RE, that will be there between base to ground. Again, base to emitter or base to ground here. between base to emitter. Then collector resistance RC is present between collector to ground. VCC is 0. It is present between collector to ground. So RC resistance is present between collector to ground. Then as it is fixed bias configuration, it is common emitter. So we have here beta IB. Beta is HFE. For hybrid equivalent circuit, it is HFE. So HFE IB, collector current is flowing into the circuit. So it is HFE IB in the downward direction, beta IB or HFE IB for hybrid equivalent circuit. Then output resistance, it is reciprocal of admittance. So it is 1 upon HOE, 1 upon HOE. Okay. So this is the approximate hybrid equivalent circuit of fixed bias configuration. Now here we are finding the different performance parameters of fixed bias configuration. First I'll explain you fixed bias configuration, then I will come to the voltage divider bias. Let us see what's the difference between the two and what to write. Then Zi is input impedance, it is RB parallel HIE. This RB resistance parallel HIE, that gives the input impedance Zi. Similarly, what will be output impedance Z0? Output impedance Z0 will be RC parallel 1 upon HOE. If we look from this side, from the output terminal side, it is a parallel combination of RC resistance and 1 upon HOE. It is RC parallel 1 upon HOE is Z0. Then voltage gain equation, this we have already obtained in the AC analysis, that fixed bias configuration. Its equation has to be memorized. So AB equation is minus R0 parallel RC divided by small r. AB voltage gain equation is minus small R0 parallel capital RC divided by small re. Right? This is further equal to, now this R0 is 1 upon HOE, right? Minus 1 upon HOE parallel RC divided by RE. That is minus 1 upon HOE parallel RC, this divided by RE. Right? So what is this RE? If you look here, HFE is beta RE. Okay, HI is beta RE. Sorry, HI is beta RE. Right? So beta is HFE. Correct? HI is beta RE. In hybrid model, it is HIE. In RE model, it will be beta RE. So HI is nothing but beta RE. What is beta? It is HFE. So HI is equal to HFE into RE. HIE is equal to beta RE, or HIE is equal to HFE into RE. So what will be RE then? HIE by HFE. Correct? RE will be HIE divided by HFE. So write it, HIE divided by HFE, that is RE. So that will be minus HFE into 1 upon HOE parallel capital RC, that divided by HIE. This is the formula for voltage gain in terms of hybrid parameters. Then current gain formula, it is minus AV into Zi by RC. That is minus of AV is minus, this one we have to take, minus R0 parallel RC by RE. Okay, minus of R0 parallel RC by RE, that is AV. Then Zi is beta RE. Zi is beta RE according to the formula that we have already calculated in the AC analysis of fixed bias configuration. This is approximate hybrid equivalent circuit of fixed bias configuration. When analyzing the fixed bias circuit in the AC analysis, we have already derived the formula, that is Zi is beta RE for the fixed bias configuration. So the same formula we have to use, beta RE divided by RC. So RE cancels, minus R0 parallel RC. So here that comes out to RC. R0 is very larger as compared to capital RC. Therefore, parallel combination will be smaller value, that is capital RC. That is capital RC into beta divided by RC. RC and RC will cancel. That will be approximately equal to beta. So beta is nothing but HFE in hybrid parameters, in hybrid equivalent circuit. Beta in RE model, the beta is nothing but HFE in the hybrid model. Okay. So these are the performance parameters of the fixed bias configuration, common emitter fixed bias configuration. Now let us move on to the performance parameters of voltage divider hybrid model, approximate hybrid model of the voltage divider bias configuration. This is the voltage divider configuration, what we are having here. Okay. In this voltage divider configuration, the RB is nothing but R1 parallel R2. This we have discussed many times. RB resistance is parallel combination of R1 and R2. Okay, so in the fixed bias configuration formulas, wherever there is RB, if we replace by R1 parallel R2, that will give all the formulas of the voltage divider bias configuration. Remember, RB is R1 parallel R2. This base resistance here, it's a parallel combination of R1 and R2. This RB resistance is the parallel combination of R1 and R2. Therefore, in the formulas of fixed bias configuration, if you replace RB by R1 parallel R2, that will give all the formulas for the voltage divider bias configuration or common emitter voltage divider bias configuration. So here we are having resistance R1, R2, right? Voltage divider is applicable here. Voltage divider formula is applicable to find the voltages, right, between R1 and R2. Then there is collector resistance RC, emitter resistance RE. Input is applied to the base terminal through C1 and output is taken from the collector terminal through capacitor C2. There is a bypass capacitor CE. The approximate hybrid equivalent circuit of the voltage divider is similar to that of the fixed bias. That's what I told. Just if we replace RB by R1 parallel R2, it will be same as that of the fixed bias configuration. Okay. So here that's R1 parallel R2, that is nothing but RB. So it is taken between base terminal to emitter or between base to ground. This junction resistance RB. So it is RB between base terminal to emitter, to the common emitter configuration. Then here we are having HIE, that is emitter to base junction HIE or beta RE, that is HIE here. Then on the output side, we are having beta IB collector current or HFE IB. Then we are having output resistance R0 is 1 upon HOE. R0 is 1 upon HOE. And the collector resistance RC. This RC is present between collector terminal to ground. That is, it is drawn here RC between collector to ground or collector to emitter, common emitter configuration. So this is about the voltage divider bias configuration, approximate hybrid equivalent circuit. Next, we have to find the performance parameters. So what is the die? It is RB parallel HIE. RB parallel HIE. RB is R1 parallel R2. Z0 is RC parallel 1 upon HOE. Z0 is RC parallel 1 upon HOE. But as the value of output resistance, that is 1 upon HOE, is larger as compared to capital RC, the parallel combination of 1 upon HOE and RC will be RC only. Therefore, we get here capital RC. Next is gain formula. That is what just now we discussed for the fixed bias configuration. That is the same formula minus HFE into capital RC parallel 1 upon HOE, that divided by HIE. Okay, it's the same gain formula both for fixed bias and the voltage divider bias configuration. Then next is how to find the current gain. We have to find the overall current gain. Now, if we look into the circuit, at the output side, we are having the load resistance, at the final resistance. Okay, here the load resistance will come here between collector to emitter, load resistance RL. Then we are having RC, and the collector current is flowing here from this junction of RC. Okay, the same is drawn here. There is RL resistance present where the load current is flowing. Then there is RC resistance. Then the collector current is flowing from the junction of this RC resistance. Then on the input side, we are having RB and RI. This is RB. Then this is RI, input resistance. Input resistance is RI. It is not input impedance, it is resistance. Okay, there is difference between input impedance and input resistance. Input impedance is as seen from the voltage terminals, input voltage terminals, whereas input resistance is as seen from the, that is the transistor terminals. Okay, this is the difference between input impedance and input resistance. Now here we have to consider the input resistance Ri. So Rb, then here we are having Ri. The base current is flowing through Ri. Okay. Then here we are having the input current II. Same is considered here. So supply current or input current is IS or II. Then RB is there. Then we are having RI. The current, input current is getting split into RB and RI. Is getting split into RB and RI. If we consider this circuit, now what is the total current gain? It is final current output divided by final current input. The final current output is, what is the final current output here? This current IL This is the final current output. The final current input is the net or the total input current is IS, the supply current or the input current. Okay, so we are writing the formula for current again as IL upon IS is equal to IL upon IC, IL upon IC. Okay, this current output just divided by input current into, this is the output current and this is the input current, IC by IB, IC by IB, then into IB by IS, IB by IS. This is the output current, this is the input current into IB by IS. That gives the ratio of output current to input current or the current gain. Now what is IL by IC? How to find IL by IC? Now if you want to find IL by IC, then we have to consider here for IL by IC this circuit. So here this circuit we have to consider. Now we have to apply the KVL to this portion. So if you apply the KVL to this portion of the circuit, what we get here? Positive to negative, right? Positive to negative. So it is the current, this current is nothing but it is getting split into IC and IL. Current flowing through RC is getting split into IC and IL. So it is a sum of IC and IL, the current flowing through RC. So it is minus of IC plus IL into RC, minus of IC plus IL into RC, that is positive to negative decrease in energy. Then come to ILRL, positive to negative minus ILRL equal to 0. So what is the equation? Positive to negative minus of IC plus IL that multiplied by RC, then minus ILRL equal to 0. Okay, now if we simplify this, then finally we will get IL by IC is equal to this one we will get. Just simplify that. I have explained in the class. IL by IC is equal to minus RC divided by RC plus RL. Okay, now RL is 0 in this circuit. Whatever we have considered for analysis, voltage divider circuit, RL is 0. We have not considered any load resistance, so it is 0. So as RL equal to 0, then minus RC by RC plus 0, it is minus RC by RC, or that is equal to minus 1. Then IC by IB. Next, this IC by IB here. So it is nothing but beta. IC is equal to beta into IB or HFE into IB. Beta is nothing but HFE. So it is IC by IB equal to HFE. Then last one, IB by IS. If you want to find IB by IS, then we have to consider this portion, IB and IS. Here again we have to apply the KVL equation. So if we apply the KVL equation to this, then we will get, so here it is the current flowing, what is the current flowing through RB? IS minus IB according to KCL, IS minus IB. So negative to positive, increase in energy, plus IS minus IB into RB, then come to RI, minus positive decrease in energy, minus IB RI equal to 0. What is the KVL equation? We have to apply KVL equation to this closed loop. So it is negative to positive plus of IS minus IB into RB, then positive to negative minus IB RI equal to 0. If we simplify this equation, then we'll get IB by IS is equal to RB divided by RB plus RI. Okay, so IB by IS is equal to RB divided by RB plus RI. That is the equation that is written here. IB by IS is equal to RB divided by RB plus RI, or IB is equal to IS into RB divided by RB plus RI. Okay, so substitute these values whatever we have calculated here. IL by IC is minus 1, so it is minus 1 into IC by IB is HFE into HFE into IB by IS is RB divided by RB plus RI into RB divided by RB plus RI. So that is what is written here. Current gain is IL by S, the same thing what I told just now. Now this is nothing but minus HFE into R dash divided by R dash plus HIE. How you are getting this R dash here? So R dash is nothing but RB, it is R1 parallel R2. So instead of RB, I am taking it as R dash. You can write it as simply RB, or you can write it as R dash. Both are one and the same. R1 parallel R2 it is. Next is this RB plus RI. So RI is, that is ZI. Okay, that is R1 parallel R2 parallel HIE. That is approximately equal to HIE. Is approximately equal to HIE. So we are getting here the value of RI as HIE. This input resistance here, if you see here, is nothing but simply HIE here. That is RI, HIE, this one. Okay, that is written here, HIE. Then R dash is RB, that is instead of RB I'm writing it as R dash. The final equation will be current gain is equal to minus HF into R dash divided by R dash plus HIE. Okay, so here we have derived the performance parameters of the voltage divider configuration. What are the different performance parameters? If they ask the voltage divider configuration, directly you can write start from the voltage divider circuit only, not necessary to explain the fixed bias circuit. Okay, just for comparison purpose to make you understand here, I have taken the fixed bias circuit and explained you all. But when writing in examination, you can draw the voltage divider bias circuit, this circuit, right? Draw the approximate hybrid equivalent model and then write the performance parameter. Just one sentence you can mention there that whatever RB is there, that is nothing but R1 parallel R2. RB is R1 parallel R2. It is in whatever fixed bias configuration approximate hybrid model is there. In that circuit, if we replace RB by R1 parallel R2, that gives all the equations of the voltage divider bias configuration. Just mention one sentence there. So after mentioning one sentence, then you can start deriving the performance parameters of voltage divider configuration. Zi is R1 parallel R2 parallel HIE. Z0 is approximately RC. EV is minus HFE into capital RC parallel 1 upon HIE divided by HIE. Then we have current gain equation, that is AI is equal to minus HFE into R dash divided by R dash plus HIE. Okay, these are the performance parameters. Next, let us take up the question number 15. That is, it's a numerical on common emitter fixed bias configuration. Question number 15. So this is a numerical which is asked in question number 15. I have put it in the form of a statement. So for the common emitter fixed bias configuration, given RB equal to 70K, RC equal to 4.7K, C1 and C2 equal to 10 microfarad, beta equal to 100, right? Find the values of RE, C resistance, small RE, Zi input impedance, Z0 output impedance, voltage gain and current gain with R0 equal to infinity ohms. Repeat the same, that is part B, taking R0 equal to 50 kilo ohm and compare the results. Okay, so I told you all there are two methods of asking. One is they can write it in the form of a statement, they can ask in the form of statement, or they can give the circuit diagram and they can ask it. There are two ways. Okay, so let us find the performance parameters here for the common emitter fixed bias configuration. So this is common emitter fixed bias configuration. Small r is 26 millivolt by IE. We know the standard formula, or IE is equal to 1 plus beta into IB. What is IB? According to the analysis, if you apply KVL to the input section, we get VCC minus VB divided by RB. Okay, so what is that? VCC minus VB divided by RB is IB. That is 15 volt given, VCC is given 15 volt minus 0.7 volt divided by RB is given in the circuit 470 kilo ohm. This comes out to 30.43 microampere. IE is 1 plus beta into IB. This will be 3.073 milliampere. Then find out RE. Once we know IE, can find the value of RE. 26 millivolt by IE. It is 26 millivolt by 3.073 milliampere. That comes out to 8.46 ohms. Next is ZI input impedance, that is RB parallel beta RE. RB parallel beta RE is the input impedance for the common emitter fixed bias configuration. First find out beta RE. Beta is given 100. RE we have found out 8.46. This will be 846 ohms. Then RB parallel beta RE. Beta RE. RB parallel beta RE. RB is given in the circuit 470K parallel 846 ohms. That will be 844.47 ohms. So what is the equation for Z0 then? Z0 equation is R0 parallel RC. That is small R0 parallel capital RC. R0 is infinity, they have given in the statement. R0 is infinity ohms. Infinity ohm parallel RC. RC is how much? 4.7 kilo. Correct resistance. So the parallel combination of these two will be the smaller value, that is 4.7K. Okay. Next is gain equation, minus R0 parallel minus small R0 parallel capital RC divided by small RE. That is minus R0 parallel capital RC will be capital RC only because output resistance is very large. So RC is minus 4.7K divided by 8.46 ohms, or that will be minus 555.55. Then current gain is minus AV ZI by RC. AB we have just now calculated, minus 555.55, minus of minus it is. Note that. Okay, it is minus of minus. If you leave this minus sign, the answer will be wrong. Okay, there is a difference between plus 99.82 and minus 99.82. Okay, so it is minus of minus 555.55 into 844.47, that is ZI, that divided by RC is 4.7K. This will be 99.82. Next, part C of the problem, we have to calculate for R naught equal to 50 kilo ohms. So for R naught equal to 50 kilo ohms, ZI is not affected by R naught. ZI input impedance is not affected by output resistance. It is same. There is no R naught term in the equation for input impedance. It is RB parallel beta RE. It is same, that is 844.47 ohms. Next is Z naught. Z naught is R naught parallel RC. So R naught is given, they have given it as 50 kilo ohm parallel 4.7K. The parallel combination of these two will be 4.3 kilo ohms. We have to find the parallel combination of 50 kilo ohm and 4.7 kilo ohm. Next is gain equation, minus RC by RE minus capital RC by small re, that is minus Z naught by RE. Okay, minus Z naught by RE. Z naught is this RC here. RC just now we have calculated Z naught, that is 4.3K. Okay, minus 4.3K divided by RE value is 8.46 ohms. It is minus 508.27. How we are getting Z naught equal to RC? Just we can see here. R naught, if we substitute as 10 times RC, okay, it is R naught parallel RC, right? R naught parallel RC, right? Now R naught is 10 times RC parallel RC. That will be RC only. Parallel combination of large resistance and the small resistance is smaller resistance. So we get here RC. So RC is nothing but the output impedance. The resistance seen from the output terminals, it is minus 4.3K by 8.46 ohms. That will be minus 508.27 here. Okay. Next is current gain equation, that is minus EV into ZI by RC. The formula for current gain is minus AV into ZI by RC. That will be minus of minus 508.27 into ZI, it is 844.47 divided by RC is 4.7K. This will be 91.32. Now, whatever values we have calculated, that is Z naught, AV, AI, with finite value of R naught, that is with 50 kilo ohms, they are less as compared to the Z naught, AV, and AI values for the R naught equal to infinity ohms. Right? Whatever Z naught, AV, and AI we have calculated with R naught equal to 50 kilo ohms, they are less as compared to the Z naught, AV, and AI, whatever we have calculated with R naught equal to infinity ohms. Okay. Right. So this is how we have to solve this example. Right. Z naught is R naught parallel RC here. R naught parallel RC. That will be simply RC. That is what we have taken here. Z naught equal to RC. Okay. Next problem. Next numerical. Question number 16. It's a problem on common emitter configuration with voltage divider bias. This is the numerical that I have asked. Common emitter configuration with voltage divider bias. Common emitter configuration with voltage divider bias. I have put it in the form of a statement. The statement is, for the common emitter configuration with voltage divider bias, given R1 equal to 82 kilo ohms, R2 equal to 5.6 kilo ohm, then RC equal to 3.3 kilo ohm, RE equal to 1 kilo ohm, right? AV equal to voltage gain equal to minus 160, R naught equal to 100 kilo ohms, beta equal to 100. Find the value of VCC. Find the value of VCC. Okay, we are supposed to find the value of VCC. Gain equation is minus R naught parallel RC by RE. This is the formula for voltage gain for voltage divider bias, common emitter voltage divider bias, AC analysis. It is AV equal to minus R naught, small r naught parallel capital RC by small re. Gain equation we know. This is the gain equation. We know the gain they have given minus 160. Substitute. Minus 160 is equal to minus of small r naught also they are given 100 kilo ohm, 100 kilo ohm. 100 kilo ohm parallel 3.3K divided by small RE. The small RE will be 19.96 ohms. Now what is this RE? It is 26 millivolt by IE, or IE is equal to 26 millivolt by RE. That is 26 millivolt divided by this 19.96, that comes out to 1.3 milliampere. VTH is equal to, if you look into this circuit, there's a Thevenin voltage, the voltage at this junction, VTH of R1 and R2. It is VTH is equal to VBE, this voltage, plus IERE. VTH is the voltage here. If you apply KVL, we get VTH is equal to VBE plus IE into RE. IE into RE. Therefore, VTH is equal to VBE plus IE into RE. VBE is 0.7 volts, it is fixed, plus IE is, we have calculated 1.3 milliampere into RE, emitter resistance, it is 1 kilo ohm. If you substitute this, we get 2 volts. VTH will be 2 volts. Now we know the formula for VTH according to the voltage divider rule. VTH is VCC into R2 divided by R1 plus R2. VTH is equal to VCC into R2 divided by R1 plus R2. Okay, VTH is equal to VCC into R2 divided by R1 plus R2, voltage divider rule. Fine. Now if you apply that formula, VCC, arrange for VCC, VCC is equal to VTH into R1 plus R2 divided by R2, or VCC is equal to VTH, we have calculated 2 volts, into R1 is 82K plus 5.6K, that divided by 5.6K, this comes out to 31.2 volts. Okay, like this we have calculated the value of VCC for the common emitter voltage divider bias configuration. Fine. So this is all about the assignment questions, students. Hope you all have understood. Any doubts here, students?
Excuse me, sir.
Yes.
Sir, 14 questions, sir. You said first we need to draw that voltage gain circuit. After that, we need to derive, na, sir.
Correct. Yes.
We need to directly start that derivation, sir. The performance parameters approximate derivation.
But you have to see the marks and write there. If they are asking for 8 marks or 6 marks or 7 marks, 9 marks like that, then you have to draw the circuit. Draw the circuit first. Draw its approximate hybrid equivalent model, and then explain. Because whatever you are explaining, whatever performance parameters you are finding, that is in according to the approximate hybrid equivalent model. That's what I told in yesterday's class also. The performance parameters, whatever you are finding for the circuits, AC analysis, they are you are finding them from the RE model, Okay. So similarly here, we are using the approximate hybrid equivalent circuit, and we are finding the performance parameters. Right? So it is necessary that we have to draw the circuit, main circuit, draw the approximate hybrid equivalent circuit, and then derive the performance parameters. Okay, but they will be asking for maybe 8 marks or 6 marks, right? If it is for just 4 marks, then you can write only the performance parameters. But they will be asking for more marks. This one, performance parameters, means either it will be for 6 marks or 8 marks. So if it has to take a weightage of that much marks, you have to draw the circuit, draw the approximate hybrid equivalent circuit quickly, and then explain the performance parameters. Not necessary to explain the fixed bias performance parameters. Don't explain that. Just write one sentence there, and then derive the performance parameters of voltage divider configuration. Okay, clear
Then
here?
first, sir, we need to first draw that approximate hybrid equivalent model, and then after that voltage divider circuit, na, sir.
Yes, correct. Voltage divider circuit performance parameters you have to derive.
Okay.
First,
After
you are
that, we need to
drawing
derive.
the, yes. First, you have to draw the voltage divider bias circuit, main circuit. Okay, like how we have this emitter follower circuit, this
Okay.
voltage divider. Just I explained it. This one you have to draw voltage divider bias circuit. Okay. Then after drawing this voltage divider bias circuit, next comes the approximate hybrid model. After approximate hybrid model, it's performance parameters. Just write one sentence what I told there, that if RB is replaced by R1 parallel R2 in fixed bias configuration, it will give all the formulas for the voltage divider bias configuration. That one sentence you will write there, and then start deriving all the performance parameters of the voltage divider bias configuration. Okay.
Right, sir. And sir, I have doubt in the second and 12th question, sir.
Yes.
That there also we have derived that ZI AI for the RE model, sir. And
Yes.
here also we have derived the same, just for voltage divider circuit, we need to just change that RE only, na, sir.
No, 1 minute. What is that question number 2? Just see, it is a derived expression for fixed bias circuit using RE model. It is not the hybrid model. Question number 2, it is the expression for fixed bias circuit using RE model. It is question number 2, assignment question. Just see there.
Yes, sir.
Correct? No. So it is the RE model you have to take, not the hybrid model. So you have to be little bit careful there whenever you are writing the answers. You have to read the question, understand, see what values are given. Okay, what values are given, what is the numerical, understand the problem or understand the question, and then start writing the answers. Don't simply directly start writing the answers or solving the numericals. Clear here?
Yes, sir.
Clear?
But both the equations are same, sir.
Equations will remain same. See, AC analysis RE model it is. So that's what I told. Relation between RE model and the hybrid model. For example, in the hybrid model we have HFE, right? In the RE model we are having beta, correct? And HIE will be beta RE. HIE is beta RE, correct? HIE in hybrid model, beta RE in RE model. So just compare there, accordingly you study and then write there. Got the point?
Okay.
Okay, fine. Any other doubts? Any other doubts there? Clear, no? I hope everybody understood here. Rutvik, understood, right?
Sir, I have another doubt, sir. 7 questions, sir.
Yes.
Miller's theorem. They have asked Miller's state and proof, sir.
Yes.
We have Miller's capacitance, effect, and summary, sir. Which should we have read? Sir?
Correct. See, first you can write the input capacitance derivation. Okay, start from the circuit, basic circuit of that input capacitance derivation. Then write the derivation of the output capacitance, because it will be asked for more marks only. They'll ask it for either 7 marks or 8 marks. Again, the weightage will be more, marks weightage. Then write the summary of that in few points. Summary of that. Okay. So even sometimes what they are doing, they are asking separately. Derive the expression for Miller's input capacitance and output capacitance. That question may also may come. Instead of asking state and prove Miller's theorem, they may ask derive the expression for Miller's input capacitance and Miller's output capacitance. There you have to explain only derive only the Miller's input capacitance derivation with the circuit, and with the circuit Miller's output capacitance. If they are asking,
sir, then you need to understand in the video that you have stated that theorem, sir.
Correct.
After that, the capacitance, output and input, we need to derive it and draw that circuit. That much only, na, sir? And
correct,
the effect.
Fine. Yes, you are right. 100%. Correct, it is. Right.
Okay, sir. Thank you.
Okay, fine. So do well. Right. Any other doubts you are having? Any other questions?
No, sir.
Okay, fine. Do well. Wish you all the best. Yes.
Sir, first question, they have asked hybrid model, na, sir. After that, H parameter for CB, CC, then CC.
Yes.
In exam, they will ask all the 3 configurations, sir, or any 2 or 1.
Sometimes they have asked. Sometimes they have asked all the 3. Sometimes they are asking only say only common emitter configuration. Just I have asked in one of the questions, common emitter configuration, right? Or they may ask common base configuration hybrid equivalent model, or common collector configuration hybrid equivalent model, starting from the generalized model. Right? It may differ. We don't know how the question may come in examination. It depends on the question paper setup. Okay. So accordingly, you have to be ready with all the part of the question, all the part of the answer, and whatever may be the answer, we should be ready to answer according to the question in the way that the question has been asked.
Okay,
clear here?
Okay.
Fine. Okay. Do well. Wish you all the best.
Yes. Thank you.
Okay.